Welcome to the Deep Dive. We're the place you come to cut through the noise, stack up the sources, and really get to the heart of what matters. Fast. Today we're digging into something truly fascinating, often called the holy grail of cryptography, homomorphic encryption. Our mission really is to unpack this. What is it? Why is it certainly so crucial? How does the math behind it actually work? And, what does it mean for our digital future? We've got a great stack of research and articles to help us figure it all out.
It's definitely a big topic because, look, we're living with this constant push and pull, right, between actually using our data and keeping it totally private. Especially now with cloud computing, AI, just data everywhere. Companies have to process sensitive stuff, but they also have to lock it down. Traditional encryption, it's good, but it has this gap. It protects data sitting still or moving across the network. But the moment you need to work with it, compute on it, you have to decrypt it first. And that's the weak spot. Homomorphic encryption, well, it promises to completely change that whole game.
Okay, let's break that down because honestly, it sounds a little bit like magic. Computation on encrypted data. How? So the core idea is you can perform calculations directly on data that's still encrypted. You don't decrypt it first. And the result you get back, still encrypted, only the person with the original key can unlock it and see the actual answer. Maybe an analogy helps here. Even for those of you who follow this stuff closely, imagine you have, some really valuable raw materials, let's say rare metals for jewelry. You need an expert artisan to work on them, but you don't fully trust anyone. You definitely don't want them touching or seeing the raw stuff. So you put your metals in this special locked box. It's transparent, so they can see the shapes, but it's locked. And crucially, it has built-in gloves.
Ah, the secure glove box analogy. Good one.
Right, so the box is locked, that's your ciphertext. The metals inside are your plaintext. You hold the only key. You hand this locked glove box to the artisan. They use the built-in gloves to manipulate the materials, assemble the jewelry, do whatever needs doing. They never directly touch the raw materials, they just work through the gloves.
Without ever opening the box.
Exactly. When they're done, they hand the locked box back. Inside is the finished jewelry, still encrypted, still locked up. Use your key, open it, and there's your result, the finished piece. That's the decrypted result.
And that analogy really nails the problem HE solves. This whole data in use vulnerability. Like you said, traditional methods cover data at rest, sitting on a hard drive and in transit moving over the internet, fine. But for data in use, when you need to analyze it, run calculations, query it, you typically have to decrypt. And that moment of decryption, often on some third-party server or in the cloud, that's the danger zone. Attackers, insiders, accidents. It's exposed. Homomorphic encryption just eliminates that window completely. Data stays protected through its entire life cycle: storage, transit, and processing.
That's a fundamental shift. And it's not just, a neat trick. Why is this becoming so critical right now? This problem's been around for ages, right? The Everest of crypto, as some called it?
It has, but several things are converging.
Okay, like what?
Well, first, the obvious one, data privacy. It's just non-negotiable now. We have to protect sensitive info, even while algorithms are crunching it.
Then there's the massive shift to outsource computation. Everyone uses the cloud, third-party analytics. It's efficient, it scales, but it introduces huge risks if data has to be in the clear for processing.
Exactly. And on top of that, you've got heavy regulatory pressure. Think GDPR, CCPA. These laws demand super strict privacy. Traditional processing of sensitive data, it's becoming legally, ethically really difficult.
So HE steps in to fix that core tension.
Precisely. It resolves that conflict between using data and keeping it secure. You can use the cloud, use third-party tools. Without that privacy trade-off, it basically gets rid of that security gap where data used to be exposed, which is massive. Because think about it. Even if a server gets hacked, if the data is homomorphically encrypted,
The attackers just get gibberish. Useless ciphertext.
right. It really changes the game for secure computation.
Okay, it sounds amazing. But how does it actually work? It's not really magic, obviously. There's complex math under the hood.
Definitely complex math. Most modern schemes rely on problems related to something called lattices.
Lattices, like a garden trellis.
Sort of, but imagine an incredibly complex, high-dimensional grid of points. Finding your way around is easy if you have the secret map, the key. But without that key, finding specific points or shortest paths is computationally really hard. Intractable, basically. That difficulty is the security.
Okay.
A key idea here is the learning with errors problem, or LWE. Oded Rejev introduced it back in 2005. Think of it like solving a bunch of linear equations. Simple enough, right? But now imagine someone adds a tiny bit of random error or noise to each equation.
Okay, that makes it harder.
Way harder. Without the secret key, figuring out the original solution becomes incredibly difficult. But with the key, it's easy again. That's the LW principle.
Got it. So that hardness is what makes it secure. How does that translate into the actual process?
Well, the workflow usually goes something like this.
Okay.
First, key generation. The data owner creates keys, a public one for encrypting, a secret one for decrypting, and often an evaluation key to help with the homomorphic math.
Okay.
Second, encryption. You take your plaintext data, encrypt it with the public key, and send the ciphertext off to wherever the computing needs to happen, say, a cloud server.
An untrusted server, potentially.
Exactly. Third, homomorphic evaluation. That server takes the encrypted data and the evaluation key, but not the secret key, that's crucial, and performs the needed calculations directly on the ciphertext. It's manipulating those complex, noisy lattice structures we talked about.
Right. Without seeing the original data.
Never. Finally, decryption. The server sends the encrypted result back to the data owner. The owner uses their secret key to decrypt it, and boom, they get the plaintext answer, just as if the calculation had been done on unencrypted data.
But you mentioned noise. That sounds like a problem. Does it build up?
It does. That's a key challenge, especially with multiplication operations. The noise in the ciphertext grows with each computation.
Like static on an old radio signal.
Good analogy. And if that noise gets too loud, crosses a certain threshold...
Decryption fails.
Yeah.
You just get garbage back.
Exactly. Which obviously limits how much you can compute.
So,
yeah.
How do you get around that for complex calculations? How do you do unlimited operations?
That was the million-dollar question. Solved by Craig Gentry in 2009 with his breakthrough, bootstrapping.
Bootstrapping. Sounds like pulling yourself up by your bootstraps.
Kind of. It's an incredibly clever way to refresh a ciphertext that's getting too noisy. Essentially, you homomorphically run the scheme's own decryption process on the noisy ciphertext. But, and this is the magic, you use an encrypted version of the secret key to do it.
Wait, you run decryption using an encrypted key without actually decrypting?
Precisely. The output is a new ciphertext. It still encrypts the same original message, but the noise level is reset back down to low, like cleaning the static off the signal without stopping the music. It lets you compute indefinitely.
Wow. Okay, that is ingenious. And that bootstrapping is what enables fully homomorphic encryption, right?
That's the key. And since Gentry's work, we've seen more efficient schemes pop up, often based on a variant called ring learning with errors RLWE.
Ring LWE. Why ring?
It uses some structures from abstract algebra called rings to pack the LWE problem more efficiently. Basically, it lets you process data in parallel, speeding things up quite a bit.
Makes sense. And there are different flavors of these schemes.
Yeah, a few main families based on RLWE. You hear about BGV and BFV. They're really good for exact math, like integer arithmetic, think financial calculations. Then there's CKKS. This one's designed for approximate arithmetic working with real numbers, like in machine learning, where a tiny bit of imprecision is okay.
Ah, okay. Useful for AI.
Definitely. And you also have TFHE, which is known for having particularly fast bootstrapping. That makes it good for things like evaluating complex logic circuits.
So this idea of noise and bootstrapping leads us to different types of homomorphic encryption depending on their capabilities.
Exactly. It wasn't an overnight jump to full capability.
Right. So first there was partially homomorphic encryption, PHE.
Yes, the earliest kind. These schemes could only do one type of operation, either addition or multiplication, but they could do it as many times as you wanted. Think Palier for addition or basic RSA for multiplication. Simple but limited.
Okay, one operation type, then what?
Then came somewhat homomorphic encryption, or SHE. Now you could do both addition and multiplication, progress, but only for a limited number of steps or a limited depth of multiplication. Because that noise we talked about would build up and eventually overwhelm the ciphertext. Gentry's first scheme was actually a bootstrappable SHE.
Got it. Limited operations. And that brings us to the goal.
Fully homomorphic encryption, FHE. The most powerful type. Thanks to bootstrapping, it allows an unlimited number of operations of any kind. Additions, multiplications, comparisons, anything. It's effectively Turing complete. You can compute any function you want on encrypted data.
Unlimited operations. That's the real game changer.
It really is, and that distinction matters. She might be okay for some fixed tasks, maybe in specific network setups like parts of 5G, but for general purpose computing, mobile networks, complex AI models, basically, most of the stuff we want to do, you need the unbounded nature of FHE.
Okay, so FHE is the goal. How is this actually being used today? Where are we seeing this magic glove box in action?
It's starting to pop up in some really critical areas. Secure cloud computing is a big one. Companies can upload encrypted databases, run analytics queries, all without the cloud provider ever seeing the raw data. Huge for privacy.
I can see that. What else?
Healthcare. This is massive. Imagine researchers wanting to train an AI model for disease prediction. They can pool encrypted patient data from multiple hospitals, run the training homomorphically, and get the model back without ever exposing individual patient records. Crucial for things like hypercompliance.
Wow, and genomic data too, I suppose.
Absolutely. Genomic analysis is a prime use case. Then there's secure financial services. Banks could, say, collaborate to detect fraud by analyzing shared, encrypted transaction patterns without revealing sensitive customer info to competitors. Private credit scoring is another possibility.
Okay, finance, healthcare, cloud. What about AI more broadly?
Machine learning as a service, alas. You have a trained model, maybe sitting with a provider like Google or AWS. A company can encrypt its own sensitive input data, send it to the provider, have the model applied homomorphically, and get back only an encrypted prediction. The MLAS provider learns nothing about the input data.
That protects the user's data completely.
Completely. And there are other cool areas emerging, too.
Yeah.
Secure e-voting. Imagine casting your vote. It gets encrypted, added homomorphically to the tally. Only the final count is decrypted. Individual votes stay private, but the result is verifiable. Also, IoT and edge computing. Data from your smart devices. Encrypted at the source. Aggregate and analyze it homomorphically on an edge server. Only send encrypted stats up to the main cloud. Protects individual privacy right from the start.
And even searching databases privately.
Right, private information retrieval or PIR. Asking a database a question without the database owner learning what you asked for. Another big step for confidentiality.
It really feels like this fills a major gap we've had for decades.
It absolutely does. We finally have the third piece of the puzzle. Data protected at rest, data protected in transit, and now finally, data protected in use.
The security trifecta, as some call it.
Exactly. And the implications are huge. No decryption needed on the processing side means no window for attackers. It supports a true zero-trust model. You don't have to trust the cloud provider with your raw data anymore. If they get breached, the attackers get encrypted junk.
That also helps with insider threats, right? Even admins can't see the data being processed.
Precisely. Mitigates insider threats. And for businesses struggling with regulations like GDPR.
It simplifies compliance enormously, I'd imagine.
Massively. And one more thing, looking forward, quantum resistance.
Ah, the quantum computing threat to current encryption.
Right. Most current public key crypto, like RSA, is vulnerable to future quantum computers. But these lattice-based HE schemes, they're generally believed to be resistant. That's a huge future-proofing benefit.
Okay, this all sounds incredible, but there have to be downsides.
Right.
It can't be perfect yet.
Oh, definitely not perfect yet.
Yeah.
There are significant challenges. The biggest one is performance overhead.
It's slow.
It can be very slow. We're talking thousands, sometimes millions of times slower than operating on unencrypted data. Bootstrapping especially is computationally very heavy.
Thousands of times. That sounds almost unusable for many things.
Well, yes and no. For some applications, it is too slow right now. But for high-value, privacy-critical tasks where the alternative is no computation at all, even slow computation is revolutionary. It enables things that were simply impossible before.
Good point. What else besides speed?
Ciphertext expansion. Encrypted data gets much, much bigger than the original plaintext. Think kilobytes or even megabytes for a single bit sometimes.
Whoa. So more storage needed, more network bandwidth.
Exactly. It also tends to need a lot of RAM, so it's memory intensive, and frankly, it's still complex. You need serious cryptographic expertise to implement and use these schemes correctly and efficiently today.
So slow, data gets huge, needs lots of memory, and it's hard to use. Quite a list. How are we tackling these?
There's a massive research effort underway, generally following a sort of three-pronged approach.
Okay, prong one.
Algorithmic improvements, smarter FHE schemes, faster bootstrapping methods, better ways to manage that noise. Also building tools like transpilers that try to automatically convert regular code into FHE code, making it easier for developers.
Makes sense. Better math, easier tools. Prong two.
Hardware acceleration. This is crucial. Companies like Intel, Samsung, startups too, are designing specialized chips, FPGAs, ASICs specifically to run FHE operations much, much faster.
Wait, graphics cards for graphics.
Exactly like that. The goal is to take that overhead from thousands of times slower down to maybe just, 2x, 5x, 10x slower. That makes it practical for way more applications.
Okay, specialized hardware. And the third prong.
Software libraries and standardization. We need good, accessible tools. We're seeing great open source libraries emerge, like Microsoft Seal, HeLib from IBM, TFHE, Palisade. These make it easier for non-experts to start experimenting. And standardization efforts are key too, like the work by the Homomorphic Encryption Standardization Consortium. That builds trust and ensures different systems can eventually work together.
So algorithms, hardware, software tools. Where does this leave us in, say, the next 5 to 10 years? What can we realistically expect?
I think we'll see FHE move out of the lab and into niche commercial use, especially in those high sensitivity areas.
Yeah.
Healthcare, finance, government. Think B2B services where the privacy guarantee is the core value proposition.
Makes sense. Will the big cloud players get involved?
Almost certainly. Expect cloud providers to start offering FHE accelerated services, probably leveraging that specialized hardware we talked about, making it easier for customers to adopt.
And maybe integrated into everyday tools.
That's the hope. Integration into databases, into machine learning platforms, so it becomes easier to just switch on privacy for certain operations. The market growth projections are pretty strong, looking at hundreds of millions, maybe more, by the late 2020s. It shows there's real momentum building.
So it's moving from theoretical wonder to practical tool.
Absolutely. The long-term vision, FHE could become almost invisible, a fundamental layer built into the internet, into the cloud, ensuring computation is private by default. A true privacy by design world. It's not just about protecting data, it's about enabling collaboration and innovation with sensitive data in ways we just couldn't before. Think about sharing medical data safely across borders for research, that kind of world-changing potential.
So wrapping up our deep dive today, it really feels like homomorphic encryption isn't just an incremental improvement, it's a genuine paradigm shift. It tackles that decades-old problem of keeping data secure while it's being processed, opening doors for innovation that were firmly shut before. It really is about unlocking potential. But it leaves us with a fascinating thought to ponder. As homomorphic encryption gets better and more widespread, letting us compute on data without ever really seeing it, what new ethical questions pop up? Think about data ownership, accountability. Who's responsible when the computations are done blindly? That's something for us all to think about in this coming era of enhanced digital privacy. Thank you so much for joining us on this deep dive into the world of homomorphic encryption. We hope you keep exploring these amazing developments changing our digital landscape.